Hello students, we are solving the IB Math A HL past papers and currently we are solving the IB Math A HL May 2022 paper 3 time zone 2 past paper. We have solved question number 1 of this paper in our previous session and today we will be solving the question number 2 of the same paper. You will be getting the links to all the previously solved questions of this paper and of the other papers in form of playlists in my channel NS Online Math Tutoring Classes. So without any further delay, let us start answering question number 2. The maximum mark is 27. This question asks you to investigate conditions for the existence of complex roots of polynomial equations of degree 3 and 4. The cubic equation x cube plus px squared plus qx plus r equal to 0, where p, q, r belong to the set of real numbers, has roots alpha, beta, and gamma. Subpart E says by expanding x minus alpha times x minus beta times x minus gamma, show that p, the coefficient of x square, is equal to negative of alpha plus beta plus gamma. Q, the coefficient of x, is equal to alpha beta plus beta gamma plus gamma alpha, and r, the constant term, is equal to negative of alpha times beta times gamma. Okay, so we have to expand this one. So subpart E, x minus alpha, x minus beta, x minus gamma is equal to, first of all, let us multiply these two binomials. X square minus alpha x minus beta x plus alpha beta and x minus gamma. So this is equal to x cube minus x square gamma minus alpha x square plus alpha gamma x minus beta x square and plus beta gamma x plus alpha beta x plus minus alpha beta gamma. Okay, so this is equal to x cube. Next, I am grouping the terms containing x square. This is a term containing x square, this is containing x square, and this is containing x square. Okay, so I am writing plus x square because this is a term containing a plus. Okay, so I am writing plus x square, and then I am this one is minus alpha, this is minus beta, and that is minus gamma. Okay, and then I will be grouping the terms containing x. This is one of the term, this is one term, this is the second term, and this is the third term. Okay, so let me start with alpha beta because I'm having you can start with alpha beta, doesn't matter, alpha gamma also doesn't matter. I'm just writing alpha beta because I have alpha beta over here, so in the front place. So alpha beta plus beta gamma plus this is alpha gamma, so I'm writing it as gamma alpha. And finally minus alpha beta gamma. Clear? Now we have to just relate this expression to this. X cube and x cube. Fine. And p is the coefficient of x square. What is the coefficient of x square? It is minus alpha, minus beta, and minus gamma. So therefore p is equal to minus alpha minus beta minus gamma, which is equal to negative alpha plus beta plus gamma. Okay. Coming to q. Q is the coefficient of x. So coefficient of x is this one. So therefore q is equal to alpha beta plus beta gamma plus gamma alpha. And finally it is r, the constant term. The constant term equal to this. Negative alpha beta gamma. So we have proved this. Okay. Subpart B. It is containing two further subparts. The I says show that p square minus 2q is equal to alpha square plus beta square plus gamma square. P was equal to negative of alpha plus beta plus gamma and q was equal to alpha beta plus beta gamma plus gamma alpha. And alpha beta gamma were the three roots of the cubic equation x cube plus p x square plus qx plus r equal to 0. Okay. So let us start with our answer for subpart B and I. P square, so it is minus alpha plus beta plus gamma whole square minus 2 times alpha beta plus beta gamma plus gamma alpha. What is this equal to? So this negative of alpha plus beta plus gamma is negative 1 times alpha plus beta plus gamma. So negative 1 whole square is positive 1. And this is alpha plus beta plus gamma whole square. Okay. So I can write this as alpha plus beta plus gamma whole square. And I'm expanding that part, the second term. It is minus 2 alpha minus 2 beta, alpha beta minus 2 beta gamma and minus 2 gamma alpha. Okay. Is equal to, now I am expanding this. Okay. If you want, I can just write it this way. Alpha plus beta plus gamma times alpha plus beta plus gamma and minus 2 alpha beta minus 2 beta gamma minus 2 gamma alpha. Okay. And this is equal to, in fact, alpha square plus alpha beta plus alpha gamma plus alpha beta plus beta square plus beta gamma plus gamma alpha plus beta gamma plus gamma square minus 2 alpha beta minus 2 beta gamma minus 2 gamma alpha. Okay. So this is equal to alpha square plus beta square plus gamma square. Okay. Alpha square plus beta square plus gamma square. Fine. And then this is alpha beta, this is alpha beta. So 2 alpha beta and this is minus 2 alpha beta. So they can cancel. Okay. This is alpha gamma and this is gamma alpha. Both are the same thing. So 2 alpha gamma and 2 gamma alpha and this is minus 2 gamma alpha. They cancel. This is plus beta gamma plus beta gamma. So 2 beta gamma and this is minus 2 beta gamma. They cancel. So you are having only this thing. Okay. Which is equal to p square minus 2q. Okay. Now coming to II. Okay, hence show that alpha minus hence. Okay, so we have to use the previous subpart. Alpha minus beta whole square plus beta minus gamma whole square plus gamma minus alpha whole square equal to 2p square minus 6q. This was p square minus 2q. Okay, so I p square minus 2q, and this is 2p square minus 6q. Uh, So I can write 2 times p square minus 2q because I need 2p square, so I'm just doubling it, doubling this part. Okay, so this should be equal to 2 alpha square plus beta square plus gamma square. Okay, but this will be giving us 2p square minus 4q, but I need 2p square minus 6q. So we have to add 2 minus 2q to this. Okay, so this is therefore 2p square minus 4q minus 2q is equal to 2p square minus 6q, which should be equal to 2 alpha square plus beta square plus gamma square and minus 2q. So minus 2, and in place of q, I'll be writing this alpha beta plus beta gamma plus gamma alpha. Okay, so now I am just expanding this. This is equal to alpha 2 alpha square, so I'm just writing alpha square plus alpha square plus beta square plus beta square plus gamma square plus gamma square minus 2 alpha beta minus 2 beta gamma and minus 2 gamma alpha. Okay, and this is equal to, now I have to show that this is equal to this square plus this square plus this square. Okay, so I have to group them. So this can be written as alpha square minus 2 alpha beta plus beta square. I've taken this, I have taken this, and I have taken that. Okay, plus beta square, I've taken this and taking this, minus 2 beta gamma plus gamma square plus alpha, I'm starting with this gamma square minus 2 gamma alpha plus alpha square. Okay, so this is equal to alpha minus beta whole square plus beta minus gamma whole square plus gamma minus alpha whole square. Okay, okay, so this is proved. We have done subpart II. Coming to subpart C, given that p square is less than 3q, deduce that alpha, beta, gamma cannot all be real numbers. Okay. Okay, so fine. So p square is less than 3q implies p square minus 3q is less than 0. Okay, and we have seen that 2p square minus 6q, which is, if I double this, it will be 2p square minus 6q, is equal to this. Okay, so therefore 2 times p square minus 3q is less than 0, because 2 times 0 is 0, or 2p square minus 6q is less than 0. Okay, so this means, which means alpha minus beta whole square plus beta minus gamma whole square plus gamma minus alpha whole square is less than 0, which is absurd. Because square numbers can be equal to or greater than 0. Okay, so therefore there should be some complex numbers, otherwise this cannot happen. Therefore alpha, beta, gamma cannot all be real numbers. Okay, consider the equation x cube minus 7x squared plus qx plus 1 equal to 0, where q belongs to the set of real numbers. Subpart D's question is using the result from part C. Part C had this condition given. The cubic equation that we had first started with was x cube plus px squared plus qx plus r is equal to 0. Okay. And subpart C said that when p square is less than 3q, and this equation had 3 roots, alpha, beta, and gamma, and not all the 3 roots can be real numbers. Okay, when p square is less than 3q. And subpart D's question is using the result from part C, so that when q is equal to 17, this equation has at least one complex root. Okay, so over here, this is subpart D. Over here, the value of p is negative 7. Okay, because p is the coefficient of x squared. So p is equal to negative 7. Therefore, p square is equal to 49. And q is equal to 17. So q is equal to 17. Therefore, 3q is equal to 17 times 3. If you need the calculator, I can come to the calculator. It is 17 times 3, which is equal to 51. Okay. So this is 51. So therefore we see, since 49 is less than 51, therefore p square is less than 3q. So there should be at least one complex root. Okay. Okay, so we have answered subpart D. Coming to subpart E, Noah believes that if p square is greater than or equal to 3q, this was p square is less than 3q. Now, if p square is greater than or equal to 3q, then alpha, beta, and gamma, the 3 roots of this equation, will all be real numbers. Okay. Subpart E has two further subparts. The I says, by varying the value of q in the equation, x cube minus 7x squared plus qx plus 1 equal to 0. Determine the smallest positive integer. Q was a real number, but over here they are asking for the smallest positive integer value of q required to show that Noah is incorrect. Okay. Incorrect. Okay, fine. So p square should be greater than or equal to 3q. Fine. So p square is greater than or equal to 3q. What is p? P is equal to -7, therefore p square is equal to 49. Okay. And the inequality is p square is greater than or equal to 3q. Therefore, 49 is greater than or equal to 3q, or q is less than or equal to 49 divided by 3. Okay, so 49 divided by 3. Sorry, 49 divided by 3, 16.33, because 16 times 3 is 48, 16 and 1/3, so it is 16.3 recurring. Fine. So, and q should be an integer, positive integer. So, q should be less than or equal to, first of all, let me write this as 16.3333. Therefore, q should be less than or equal to 16. Okay. And because it has to be the smallest, you have to give the smallest positive integer. It has to be a positive integer. Therefore, it should be, its smallest value should be equal to 1. So the q value can be between 1 and 16. Okay. Fine. Now we have to just get the equation, get the value of q, the smallest positive integer value of q, for which you don't have all three real roots. Then only we can say that the Noah's assumption is, or Noah's belief is, incorrect. Okay, so let me just write the equation once more over here. X cube minus 7x squared. I'm just copying so that I can see. Qx plus 1 equal to 0. Okay. Now I am bringing in the calculator and I need the graph. Add graphs. Okay, so it is x cube minus 7x squared, 7 times x squared plus qx. So let me start with 1 because q's smallest value of q is 1. Okay, so let me start with 1 plus 1 times x plus 1. Okay, and let me graph this. We are having 3 zeros, so all 3 zeros are real numbers. So for q equal to 1, all the 3 zeros are real numbers. Noah's belief is correct. So let us just go on changing the value of q. This time I'm changing the q value from 1 to 2. It is 2. Oh, and sorry, it has got changed. My goodness. I come to 7 x cube minus 7x squared plus this one is 2. Why does it go on changing? X squared. Rather, I have to put the multiplication sign 7x squared and plus this time is It is 2 times x and plus 1. In place of q, I have substituted 2. And let me press enter. Again, I am seeing this is the equation. So again, I am seeing there are 3 real roots. So let me just go again and change the equation. And this time it will be this. Okay. X cube. What all are happening? X cube, I have to change this. X to the power of 3 minus 7x square and plus, this time I'll be taking the q value as 3. Again, 3 roots. Again, I'll be changing and most probably again I have to start from the very beginning. Yeah. X cube minus 7 times minus 7 times x square plus, previously it was 3, you see 3. Now I will be taking the 4 plus 4x plus 1, enter. 3 roots. Again, I have to type in the entire thing. I'll be taking the q value as 5 in this case. This is plus. Okay. 3 roots. No change. Maybe definitely the values of the zeros are changing, but they are all real numbers. So this is this plus in between. Fine. Same thing. 3 real roots. So 7 plus. Okay, and oh, sorry. This is x square. If this one was correct. Okay. Okay, fine. Same thing continuing. And okay. Yes. Yes. Again, the same root. Same 3 real roots. Not same, but 3 real roots definitely. I don't know how long I have to continue. 8 and then 9. 3 roots. And then it will be 10. It is plus in between. 3 roots. And this is plus 3 roots. Okay. 12x plus 1 Okay. Do you see that it has moved up? Let me change the settings. You will be able to see the, let me change the y uh, minimum and y maximum values. Okay. I think that will help. Y minimum, let me take this to -4 and y max, let me take this to 2. Oh, but at least you can see very well that this is not a 0. It is not touching the x-axis. Okay, it is above the x-axis. There is one 0 but where it is crossing the x-axis and coming down. But this one, the minimum point is, local minimum point is above the x-axis. So this is not a 0. Okay. When that, and this is happening when x equal to, sorry, q is equal to 12. Let me see, q can be up to, q can be any number up to 16, right? So let me just check with 13 what happens. It's gone up. Oh, see again, it has gone up to this level. So there's only a single real root. So x equals, sorry, q equal to 12 is the smallest positive integer value. Okay. And using graphs, it is containing only 2 marks, so you don't have to draw the graph to show. So using graphs, the smallest positive integer value, value of q is equal to 12. Okay. I explain why the equation will have at least one real root for all values of q. One way of saying this is the shape of the cubic graph. Okay. So a cubic graph has one of the following shapes. This is one. It can be like this. It can be two. It can be like this. It can be like this. It can be like this. It can be over. Always you are seeing the graph is coming down. So there should be at least one root. Over here you are having, this is a repeated root and this is the third root. But at whichever way it comes down depends on the uh, sign of the term containing x cube, but it will be coming down definitely. So it has to cross the x axis. Therefore, it will be having one real root, at least one real root. And it can be this way, it can be this way. So this is the graph of x cube. This can be this way. This can be like you can draw whatever shape you want, but it will be always crossing the x-axis. Okay. And I have taken the turning point above the x-axis. I can take that below the x-axis also. This way, this way means you can you can show these. Okay, you can show this. But this is the graphical explanation. Okay, so therefore it is crossing the x-axis. Why is it not writing? X-axis at least once every time. Therefore, it has at least one real zero. Okay, this is the graphical reasoning. And if you have to go by algebra, you can say that since since the coefficients, that is PQ, are not yeah, and the 1 for the x cube term are all real numbers, therefore if there is a complex root, its conjugate will also be a root. Okay, therefore the third root will be real, or else there will be three real roots. Okay, so this is the answer for EII. Now consider polynomial equations of degree 4. The equation x to the power of 4 plus px cube plus qx squared plus rx plus s equal to 0, where p, q, r and s belong to the set of real numbers, has roots alpha, beta, gamma and delta. In a similar way to the cubic equation, it can be shown that p equal to negative of alpha plus beta plus gamma plus delta, q equal to alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta, r equal to negative of alpha beta gamma plus alpha beta delta plus alpha gamma delta plus beta gamma delta, is equal to product of alpha beta gamma and delta. So subpart F is containing two further subparts. The I says find an expression for alpha squared plus beta squared plus gamma squared plus delta squared in terms of P and Q. And over here, we are not seeing any square term. So we have to get this in terms of P and Q. So let us start with squaring P. Okay. So P square is equal to negative of alpha plus beta plus gamma plus delta whole square, which is equal to alpha plus beta plus gamma plus delta whole square. Okay, because negative 1 whole square is positive 1. And now I have to expand. Alpha plus beta plus gamma plus delta. Alpha plus beta plus gamma plus delta. Okay, so alpha square, I start with alpha and I'll be multiplying this alpha with all these four terms and then with beta and so on. So alpha square plus alpha beta plus alpha gamma plus alpha delta. Sorry, delta. And then plus beta alpha. Beta alpha, I'm writing it as alpha beta plus beta square plus beta gamma plus beta delta plus alpha gamma. Gamma alpha, I'm writing it as alpha gamma plus uh, beta gamma because I'm having beta gamma. So beta gamma plus gamma square plus gamma delta plus alpha delta plus beta delta plus gamma delta plus delta square. Okay. So this is equal to alpha square plus beta square plus gamma square plus delta square. And then alpha beta and alpha beta. So plus 2 alpha beta, then what is it? Q, right? First one is alpha beta, then is alpha gamma, right? So alpha gamma over here, alpha gamma, and this is alpha gamma plus alpha gamma. Then it is alpha delta. Alpha delta over here and alpha delta over here plus alpha delta. And then beta gamma. Okay. Beta gamma plus beta gamma and then beta gamma, beta delta is this and beta delta is that plus beta delta and plus gamma delta. Okay, fine. So we have to get the alpha square plus beta square plus, and what is this? This is Q. Okay, so therefore alpha square plus beta square plus gamma square plus delta square is equal to p square minus, I'm taking this part to the left side, which is 2q. So p square minus 2q. Okay, this is the expression for the subpart I. And coming to I hence state a condition in terms of P and Q that would imply x to the power of 4 plus px cube plus qx squared plus rx plus s equal to 0 has at least one complex root, contains a single mark. Okay, so over here in the previous, I don't remember the subpart, most probably in subpart C or something, we had shown that p square is less than 3q means p square minus 3q is less than 0, and p square minus 3q was, so far as I remember, the one expression that was equal to alpha minus beta whole square plus beta minus gamma whole square plus gamma minus alpha whole square. So that was equal to the sum of some square numbers. And if it is less than 0, sum of real numbers when squared will not be less than 0. It will be either equal to 0 or greater than 0. So that implied that all the three roots were not real. Over here also, Miss, they have not stated the condition in this case, but we have just now got this, and this is the this is just the first subpart of the same subpart. So this you have to understand, Miss. I otherwise you are simply at a loss. You don't know what condition you have to give. But because you are just prior to attempting this question, you have attempted the I subpart. So that shows that that is giving you the hint that you have to use the subpart i's answer, and you are seeing that the subpart I is having e square minus 2q equal to the sum of four square numbers. So what is the condition? Let me write. So if I it will be if p square minus 2q is less than 0, then implies alpha square plus beta square plus gamma square plus delta square will be less than 0, which is absurd for or absurd when all alpha, beta, gamma, and delta are real numbers. Okay, let me write the thing. Okay, therefore, one root should be complex number. Actually, it is at least. Okay, because P, Q, R, and S, you see, these are real numbers. So, because these coefficients are all real numbers, then if a complex root exists, then it will be existing in pair. Its complex conjugate will also be another root for this the fourth degree equation. Okay, so we have solved subpart F. Use your result from part FII. The result for part FII was p square when p square minus 2q was less than 0 for this fourth degree or quartic equation. When p square minus 2q was equal to less than 0, then there existed at least one complex root. Okay, and you have to use this result to show that the equation x to the power of 4 minus 2x cube plus 3x square minus 4x plus 5 equal to 0 has at least one complex root. This is just containing a single mark. Don't get confused with this. This will be needed later on. This was for the cubic equation when the cubic equation contained at least one complex root, and this is for the quartic equation, that is this case. Okay. So this is for G. Okay, this is the equation. So what is the value of P? P is equal to -2. And what is Q? Q is equal to 3. So P square minus 2Q should be equal to -2 whole square minus 2 times 3, which is equal to 4 minus 6, which is equal to -2, which is less than 0. Okay, therefore, there is at least one complex root. Okay. Now the equation x to the power of 4 minus 9x cubed plus 24x squared plus 22x minus 12 equal to 0 has one integer root. Okay, it has one integer root. They are saying, okay. H I, it is containing three subparts. I is state what the result in FII tells us when considering this equation. I was, as I had said, that when p square minus 2q was equal less than 0, it contained the at least one complex root. Okay. So let us check HII. Sorry, I, only I. So over here, p is equal to -9 and q is equal to 24. Okay. And we have to find out p square minus 2q. So p square minus 2q is equal to -9 whole square minus 2 times 24, which is equal to 81 minus 48. Don't have to get the actual difference, the number, after subtraction, but we can straight away see that p square minus 2q is greater than 0 because 81 is greater than 48. So since p square minus 2q is greater than 0, state what result in part FII tells us uh, when considering this equation. Uh, The subpart FII does not tell us anything. Because it tells us when it is less than 0, it should be having at least one complex root. It doesn't say when it is greater than 0 what will happen. The equation may or may not contain a real root, or sorry, a complex root. Okay, so this is the answer for the I. Subpart I, coming to the subpart I write down the integer root of this equation. Okay, for this we have the calculator. Let us graph this. Okay, let me just write this equation over here so that I can see x to the power of 4 minus 9x cubed plus 24x squared plus 22x minus 12. Okay. Oh, okay. X to the power of 4 and then minus 9x cubed minus 9 times x cubed and plus 24 times x squared plus 22x minus 12. Enter. Okay. And integer root. Definitely this is not an integer, but anyway, I can get both the roots. This is one of the roots, and this is the other root. See, this is not an integer root. This one is the integer root. So x equal to -1. Okay. So this is written. Okay. So this is I. X equal to -1. This is the integer root. Fine. I. By writing x cube as x to the power of 4 rather, minus 9x cube plus 24x squared plus 22x minus 12 as a product of one linear and one cubic factor, prove that the equation has at least one complex root. Okay. So since x equal to -1 is a root, therefore x plus 1 has to be the factor, one of the factors of this, using the factor theorem. Okay. So let us, and I have to, that will be the linear factor, and I have to get the cubic factor. In order to get the cubic factor, let us do the algebraic division. Okay. So it is x to the power of 4 minus 9x cube plus 24x square plus 22x minus 12. Okay, it is x plus 1, and it is if I take x cube, I have to take x cube because I'll be taking the first term of the divisor and first term of the dividend, and I'll be dividing the first term of the dividend by the first term of the divisor to get the first term of the quotient. X to the power of 4 divided by x is x cube. And then I will be multiplying this first term of the quotient with every term of the divisor and writing it in the next line. So x cube plus x times x is x to the power of 4. And I'll be writing below the like terms. So x cube plus 1 is x cube. And I will be subtracting, so the signs will be getting changed. And this was in fact minus. So these two are getting cancelled. These two are cancelling, and this is minus 9x cube, and this is minus x cube. So it is minus 10x cube plus 24x square. Again, this becomes a new dividend. The first term of this new dividend is minus 10x cube divided by x, which will be giving us minus 10x square as our next term of the quotient. So minus 10 x squared times x is minus 10x cube and minus 10x square. So again the signs will get changed. So it is 24 plus 10 is 34x squared plus 22x, and 34x squared divided by x is plus 34x. So 34x squared plus 34x, subtraction, so the signs will change. 34 minus 22 is 12, so minus 12 x and minus 12. So minus 12x divided by x is minus 12. So it is minus 12x. Minus 12 times x is minus 12x, and minus 12 times 1 is minus 12. Signs change, and this to cancel. So a 0 as the remainder. Okay, fine. So this is in fact equal to, let me write, therefore x to the power of 4 minus 9x cube plus 24x squared plus 22x plus x minus 12, right? Yeah, minus 12 is equal to x plus 1 times x cube, the quotient, okay? X cube minus 10x squared plus 34x minus 12. This is the linear factor, this is the cubic factor, okay? So now they are saying, prove that the equation has at least one complex root. So x plus 1 will be giving us x equal to negative 1, which is the real root that we have found. And uh, from here, this is the cubic part. And we have tackled a cubic equation previously. So, and it said that when you had this condition, and the equation was what? It was x cube plus px squared plus qx plus r is equal to 0. This was the cubic equation, okay? When we had this type of a cubic equation, the roots were alpha, beta, and gamma, and when this condition was satisfied for a cubic equation, when p square was less than 3q, we have seen that the equation contained at least one complex root. Okay, so now we will be taking this one and not this one, because it is no more a quartic equation of degree 4. It is a cubic equation, cubic factor. So we will be taking this condition. This p square is less than 3q. First of all, let us find the values of p and q. So over here, from here, therefore p is equal to minus 10 and q is equal to 34. Again, I am showing p square is less than 3q. P square is less than 3q. Okay, so let us see. Therefore, p square is equal to 100 and 3q is equal to, let me go to the calculator part, 3 times 34 is 102. Okay, so therefore p square is less than 3q, is satisfied. Hence, the equation contains at least one complex root. Okay, so this was the answer for the subpart H. I subpart of the subpart H. This was the final subpart of this question number 2. And thank you for staying with me till the end. I am Nilanjana Sanyal. I am an online IB Math A, SL and HL level tutor. I tutor students from both within India and outside India, and I offer both one-on-one and small group online tutoring services to my students. As you're seeing, I am solving the IB Math A HL past paper questions, and I'm uploading these videos in my YouTube channel. In case you're liking my videos, please do give this video a like, and please do share this video with your friends so that even they can get benefited by watching this video. And in case you have not subscribed to my channel till now, please subscribe my channel. It will be motivating me to make more math videos for you. I will understand that I am being able to help you. So that will be a motivation for me. And we meet again very soon. And of course, if in case you have any confusion, any question related to this question number 2, any confusion, any query, please feel free to write to me in the comment section, and I will be happy to help you. And we meet again very soon in our next session, where we will be taking up a new paper. So till then, bye.